No.
So today I'll speak more systematically about isometries of Hadamard spaces. So we want to understand these isometries for two reasons. I mean, okay, for many reasons, but what we need to, so we saw that if we have a manifold, we look at the 16 decomposition, and the thin part, locally it looks like locally it's a union of convex sets with smooth boundary, which are the sub-level set of the displacement function. T gamma 1 less than epsilon, D gamma 2 less than epsilon, and so on. So these are in the universal cover, these are convex sets with smooth boundary, and we want to understand first. We need to understand the boundary, how complicated it is. I mean, here it's nice, but what happens in corners? And secondly, we want to somehow, the idea is that we would like to show that we can deform the manifold, or the manifold minus some subset which we can control, to the thick part. So we want to show that we can define a flow or a vector field on the manifold which will take us to the thick part. So everywhere where the injectivity is thin, we have some preferred direction where we can increase the injectivity radius. So, and the information that we have from the Margulis lemma is that all this, when we look at displacement less than epsilon, when epsilon is the Margulis constant, then the group generated by the involved isometries is almost nilpotent. So this is so there are a lot of commutativity. So this we would like to extract this information. But first, I mean, for one reason is to define this vector field, and for another reason is to understand this angle at the corner of the boundary. And what we have is a Margulis lemma. But first we start with a systematic description of isometries. And for this I will follow the relevant chapter in the book of Baumann, Gromov, Schroeder, manifold of non-positive curvature. And there is a chapter of isometries, a group of isometries. So first there are the types. So we have four types of isometries. One elliptic. So this means that so X will be the Hadamard space, and this will mean, and we have an isometry gamma.
So X is simply connected or locally?
X is a simply connected, actually diffeomorphic to, it's untractable, diffeomorphic to Rn, when n is the dimension of X, and it's and gamma is an isometry, and so gamma is elliptic if fixed gamma is non-empty. So it has fixed point inside X. This is a set of fixed points inside X. And gamma is hyperbolic if mean gamma is non-empty, but fixed gamma is empty. So if you want, mean gamma is by definition the set of all x in X such that d gamma of X equal to the infimum of this function. but so we assume that this is non-empty, but fixed gamma is empty, so the infimum of the gamma is strictly positive. So if you want, if gamma is elliptic, then fixed gamma equals mean gamma. So these two types are the types where the minimum of d gamma attained, the infimum attained, and these two are called semi-simple. And in the linear case, when we discuss symmetric spaces, these are comes exactly for semi-simple matrices, so matrices which are diagonalizable over the complex. The third type are parabolic or strictly parabolic. Strictly parabolic. It's when the infimum of d gamma is when the infimum is 0, but not attained. So then it's strictly parabolic. And the third type is the fourth type is they sometimes call it parabolic and sometimes mixed. Parabolic or mixed is when we have only this condition. And the gamma is not necessarily 0, so it's not. Let's assume that it's positive. So if you say parabolic, you also mean, okay, let's say that if this condition, then it's not strictly parabolic, but we also want mean gamma is the minimum. So the minimum is not attained, then it's but the infimum is positive, then it's mixed, and if you want.
What's written after parabolic down?
Here, mixed.
Mixed.
It's mixed. It's called mixed because the example of such is if you have an isometry, if x is h2, so here is the example, x is a product, let's say h2 cross h2, and gamma is gamma 1, gamma 2. Well, gamma 1 is hyperbolic, that's with some translation on an axis, but gamma 2 is parabolic. Then the gamma, which consists of both, is neither hyperbolic nor parabolic, so it's mixed. So it's the infimum is not attained, but the minimum is strictly positive. The infimum is strictly positive. Okay, so these are the four types. And this corresponds to, if you want to isometries that have fixed point at infinity, we will see that. And sometimes the set of fixed point is complicated at infinity. For instance, if you think on this mixed parabolic, not strictly parabolic, try to think what is the set of fixed point of this isometry on the boundary. So it will be circle. So the boundary here is a three-dimensional sphere, and there will be a circle here that is fixed by this isometry. Right.
Why?
What?
I mean, you have 2 points
Is it a
here and 1 point
circle,
here, right?
Is it a circle? Oh, maybe half circle. No. Yeah. What is this actually? So So first try to think what is the boundary here. So the boundary of H2 is a circle, the boundary of this is a circle, but then you need somehow to attach them, so this is a sphere. If this is a hyperbolic isometry, then it has two fixed points in the boundary of H2. This is parabolic isometry, then it has one fixed point. And okay, so it will be half circle. Okay, think about it. It's a nice exercise. Just to understand the fixed point at infinity of isometry. Yeah, actually, it cannot be. It cannot be too complicated. But it's okay. So let's. I follow mostly a chapter, the relevant chapter in this book, Van Schroeder, but I will add some lemmas that are not here and we will need later. But first, lemma. First, I need the RAM decomposition for subsets. So in general, consider M inside X. M is not a good notation. Yeah. So let's call it Y. Y is a closed convex. And suppose that gamma is the isometries of X such that gamma preserves Y. So Y is gamma is Y. We need to consider this case for inductive argument. So we'll need not just to think of isometry of the full space, but restrict the isometry to a convex subset. So first, we have the RAM decomposition also for closed convex subsets. So this is a lemma. Any such Y, so closed convex set, decompose canonically to Y1 cross R to some L with L maximal, where L is maximal, and any isometry of Y. So this is isometrical decomposition, respect this decomposition. So we talked about isometry here and isometry. So this is a lemma I don't want to prove. It's not maybe I should call it a fact and then I don't need to prove lemma. But I don't want to prove because it's really it's almost obvious if you think about it. Okay, maybe I'll tell you how do you define such a Y. So you look for a Euclidean, totally geodesic Euclidean subspace such that sorry. Yeah, I mean, maybe you should say any okay. So you find some maximal totally geodesic flat subspace such that at any point in Y you have a parallel to the subset. That's how. Maybe there is no such thing, but if there is, you look for a maximal such thing. And then, if you have a parallel at any point, then the space must decompose.
Is Y1 a subset of F? Even though it's actually set like.
Okay, if you fix some Y0, any such y and y0 is a point in y, then you decompose canonically, and then decompose canonical, and then you can suppose that y contains y0 is a subspace. Y1, yeah. You can fix, you can, if you fix some point, then you can choose y1 to be a subspace of y, which contains, this is how you prove it. So you fix it, you take some point, and you look at a maximal totally geodesic Euclidean flat subspace inside y through this point, such that at any other point you have a parallel Euclidean space. And then this gives you a decomposition, and then you show that it must be unique and invariant up to isometries, because if it's really on the level of an exercise. You can read it in the book. It's half page. The argument somehow I want to go on to other stuff, but this is really, if you think about it, it's not hard. I think you have to rely on the flat strip theorem. Okay, let's assume that maybe we'll come back to this, like this course is like the way of teaching is like coloring a wall. So each time we give more color, we don't give all the details at the first time. But let's suppose that. And
Can L be 0?
what?
Can L be 0?
Yeah. In most cases it will be 0. For instance, if y is a bounded set, then it's then this is trivial.
Y is bounded, then it's always.
If y is bounded, then y equals y1. So there is no Euclidean factor inside the bound set. But even if it's not bounded, it doesn't have to be.
Oh, it's closed. Okay.
This is.
I mean, if X is Euclidean, what do you require of Y1? I don't try to understand this.
I don't think y1 is a closed convex. Y1 is also, if I don't require anything of it, but it will be closed convex subset of y.
Okay.
Okay. But okay, this I didn't want to prove, but most problems today I will prove. But this, try to prove it yourself. Again, so gamma is in the isometry group of, let's say, let's say of y. Then if gamma is elliptic, one of them is y, no? The first or the second?
No.
It's like that?
That's right.
Gamma is elliptic if and only if gamma is the orbits of gamma are bounded. So if you want gamma to the n x n in z is bounded.
So is gamma in the isometry of y, or it's isometry of x that fixes y?
So now gamma is in the isometries of y. But
So it doesn't have to be an element in the isometries of x, like above.
No, not necessarily, but not necessarily. But we will always consider isometries of x and restricting to y. So
I mean, it's bounded for every X? Or?
yeah, if it's bounded for one x, first it's enough that it bounds for one x and then it's bounded for every x, and because the distance between 2 points. So this is one thing. Two, if gamma is elliptic, then mean gamma, which is actually fixed gamma, is totally geodesic. Submanifold. Here, okay, here I assume that totally geodesic. Okay, what do I mean by totally geodesic? Okay, it's convex. It's convex, of course. And if y is everything, then fix gamma is totally geodesic. Hadamard manifold. And third thing that if gamma is non-trivial, then fix gamma is dimension is strictly small.
You mean dimension of y or?
Is that in y1? I mean the first one?
Sorry?
For x in y or x in y1? X in y1. I assume.
Wait, no. Now there is no y1. Now there is this lemma is independent. So actually, let's still take isometries of x. Forget about y. For this lemma, I don't think it's important to take one. And then yeah, forget about y. In this lemma, we don't need y. And later we will. This lemma is about elliptic isometries of x. And first I said that yes, it's three parts. First, that an isometry is elliptic if and only if the orbits are bounded.
So what events? For what events gamma is just being a shift? Like if x is just a line, and you just shift.
And it's not elliptic.
Shift is not elliptic.
Oh, it's
Elliptic means that
okay,
there is a
okay.
fixed point.
So
And then the fixed point is a totally geodesic submanifold. It could be trivial, it could be zero dimension. And this is obvious if the dimension is smaller, if it's not bigger. So you know the proof of this? One, the idea is to take the circumcenter. So okay. This is one. If gamma is elliptic, let x0 be a point in fixed gamma, and then for any x distance and any n, and the distance of gamma n x is most distance of gamma n x, gamma n x0 plus distance x0 to x, which is twice the distance x0, so it's fine. And conversely, if some point x is bounded, let x0 be the center of this set. So I told you that every set has a unique Chebyshev center. You remember the definition? You don't remember? So Chebyshev center, by definition, center.
So we said a gamma to the z
you remember what is center? Center of the bounded set, if B is bounded, is defined as follows. So let B in X be bounded. So first you define the R of B is the infimum over all R bigger than 0 such that there exists a ball there exists X in X, not necessarily in B, such that the ball around X of radius R contains B. So this is the radius of B if you want. And then you define center of B to be actually it's a unique point. Then you show that there is X in X such that the ball around X of radius RB contains B, and it's unique and exists and unique. And the reason that if there were two, then you can take the midpoint of them, and then a ball of smaller radius around the midpoint would contain B. So first, why there is such the idea is the proof is from uniform convexity. You take a sequence Rn to be Rb plus 1 over n, and then choose some xn such that the ball of radius Rn around it contains B. And then this sequence, you show that it must be Cauchy, so it has a limit, and then you argue that the limit is unique because otherwise the midpoint will give you a better center. But again, this I will skip the proof of that today. I assume that you know it. So then, if you for every bounded set, you have a center. So if you have a bounded orbit, the center of this orbit is a fixed point. If you have a bounded orbit, then you are limited. Now, we show we claim that the fixed point of gamma is a totally geodesic submanifold. Okay, so actually I don't really argue about it. I just say that it's obviously convex because the displacement function is a convex function. So the fixed set of the displacement function is a convex set, and it's obviously closed but why is it a manifold? You need to show that if you fix some segment, then you fix the whole geodesic. And from what this follow? I mean,
Yeah, triangle inequalities.
why if you fix 2 points, then you must fix. I mean, if the metric is analytic, then of course. If the but for this they don't need the metric to be analytic. What?
Yeah, maybe
Ah,
it's triangle
wait. Yeah,
inequality.
of course. Yeah, this geodesic goes to some geodesic, and yeah, if 2 geodesic coincide in the interval. So, of course, yeah, that's obvious. Okay. And I thought you take this geodesic to some geodesic, but if 2 geodesic coincide on an interval, then it coincides. Sorry, I was the metric is C2. It doesn't have to be analytic. Yeah. Okay. So this about elliptic elements. Okay. Now another lemma. Again, y inside x is closed convex, and pi y is denote the nearest point projection. So for any x in x, there is a unique nearest point inside y. It's similar to the proof of this existence of center. For any x in x, you find the nearest point by taking a sequence which at the limit minimize the distance between the point and the set, and then you show it must be Cauchy and converge to a point, and you show that this point must be unique because otherwise the center will be, if there are 2 points, then the midpoint of both will be strictly closer. Both arguments use the fact that the Hadamard manifolds are at 0. So the triangles in the Hadamard manifolds are thinner than Euclidean triangles. But again, I don't want to spend too much time on this here. So there is the nearest point projector is a continuous retraction. It's a retraction. And it's one Lifshitz if you want the distance between pi y x1 pi y x2 less than equal the distance between x1 and x2. Okay, now dilemma. If gamma is an isometry, preserve y, then gamma commute with pi y. Then gamma commute with pi y. D gamma of pi y x is smaller or equal to d gamma x. And equality implies that d gamma is constant on the interval between pi pi y x to x. And 1, 2 follows that gamma and gamma restricted to y are of the same type. So what means that if gamma is elliptic, then gamma restricted to y is elliptic. If gamma is parabolic, then gamma restricted to y is parabolic. If gamma is hyperbolic, then gamma restricted to y is hyperbolic. So they have the same type. And if gamma is semi-simple, then mean gamma intersection y is non-empty, and if gamma is parabolic, then, by the way, if gamma is parabolic, y cannot be bounded. Then if d gamma equals inf d gamma restricted to y. And if you want parabolic, okay. So what do I need to prove? What is not obvious? The fact that gamma commute with pi y is obvious or not? Obvious. So we have, let's go with, we have y. Here is x. Pi y is the nearest point to x. Here is gamma x. And this must be gamma of pi y x. Must be the nearest point. Because it's an isometry, the nearest point is a geometric property, so it must observe that. So the gamma commute with pi y, and therefore, because pi y is a retraction, it is a contraction, shrink distances, then we have this, right? The distance, by definition, d gamma of x is the distance between x and gamma x, and d gamma of pi y x is the distance between pi y of x to gamma pi y of x, which is the same as pi y of gamma x.
No.
Then that's it. Because pi y, yeah, because it shrinks distances. So, and now if you, and okay, and if there was equality here, because d gamma is a convex function, and you look at d gamma from here to here, it's convex, and this proof actually shows that it's monotonic. If you start to go from here to this direction, then it's monotonically increasing, monotonically non-decreasing. So if it's the same, attain the same value here and here, it must be constant. So if we have equality,
Why is it monotonically non-increasing?
suppose you have a geodesic C of t, and C of 0 is this point, and C of 1 is this point. So this point is the nearest point projection of C of t. So exactly the same thing that we said about x, you can say about C of t. The distance between of these two is at least this distance. So all the way, it's in okay. And each one of this is at least this. Y. Okay. And we know that it's also convex. The convex function.
It's a convex function which has 2 points which are the same. So same
In
value.
general, a convex function can have to. It doesn't have to be constant. It can have the same value twice. But if it's but since this is the minimum, then and then it's come back to the same. That must be constant. So if it's equality, then they're equal on the interval. And by the way, if we knew that the metric is analytic, then they will be equal all the way to infinity. Actually, yeah. No, actually, we don't need it. Okay. Now, again, the fact that it shrink distances also imply this, that the mean gamma, the minimal value is attained on y, right? So, if it's semi-simple, then we know that. But why is it of the same type? Okay, this implies that it's of the same type. I mean, for any x in the space, d gamma of x is at least d gamma of pi y x. So if x is the point where the minimal value attained, then also pi y of x is the point where the minimal value attained. Which means that if gamma was semi-simple, then the restriction of gamma to y is also semi-simple. And if x was a fixed point, then pi y of x is also fixed. And so therefore, if gamma is semi-simple, the restriction of gamma to y is semi-simple, and the minimal set is the shape. And if it's elliptic, then the restriction is elliptic. Okay? And if the minimum was not attained, then it cannot attain here also. On y. So if it's parabolic, or strictly parabolic. Okay, so I think we are happy about this level. Yeah. I'm not used to follow it. So it's confusing. But I looked at the book and they have so many valuable data about the isometry, so I said why not following it here. And, okay. By the way, notation. If you have 2 points x1 and x2 in x, we denote the midpoint by x1 plus x2. It's not a linear space, but I think it's a good notation of a midpoint. The midpoint is a unique point, such that the distance to x1 and the distance to x2 is the half the distance between x1 and x2. And okay, so here is another lemma. If y is the midpoint at y, the midpoint of x and gamma x, then d gamma of y is less than d gamma of x. And equality implies that that x is in the minimal set of gamma, and if further gamma is hyperbolic, then the geodesic gamma x, then the geodesic, let's call it span x gamma x, so it's a geodesic, unique geodesic that contains 2 points. Its gamma is gamma invariant. Later we'll see that a geodesic that is gamma invariant is an axis of gamma. Gamma acts on it by translation, and all these geodesic are parallel and so on, but for now I only say this. So in each particular it means that it's an axis.
So if the minimum is not zero,
What?
if the minimum is not zero, otherwise
Yeah,
it's a constant.
if I said if gamma is hyperbolic,
Hyperbolic,
means that
okay.
it's not an
Okay, I thought if x is hyperbolic. Then
yeah. Okay, let's say it already. So if gamma is hyperbolic, then mean gamma is a convex set of the form is a convex set of the form W cos R, and gamma on which gamma acts by let's say gamma prime translation. So this is a set of consists of many parallels of one geodesic, and is isomorphic to and gamma acts trivially on this factor and by translation there. So that's our hyperbolic.
So gamma prime is trivial?
What? Gamma? Yes, sorry. Gamma acts by ID translation. Another thing, gamma and gamma A, from M and N, gamma and gamma M are simultaneously, at the same time. Okay, I hope the same. Gamma and gamma M of the same type. And
if they are parabolic, they have the same fixed point in infinity.
Yeah. Now it could be that gamma to the m is more fixed point than gamma. It could be that, for instance, suppose that gamma is a reflection, gamma square is identical. It could be that gamma has more fixed points, but they are of the same type. Okay, so what is the idea? The idea here in one is that so if you have x and you have gamma x, and this is the midpoint y, and then you have gamma square x, and this will be gamma y. So you see that this distance is smaller than this. Except but you see that by the triangle, this is half the segment, and then again half the segment. By the triangle inequality, the distance between y to gamma y is smaller than the distance between x to gamma x. So this proves the first claim. Except when there is equality, equality will be equality implies that we have the following picture: x, gamma x, and the angle here is exactly pi over 2. Right? That would
Pi.
pi. Yeah. The angle must. The equality implies equality between the distance implies that it's a continuation of the same line. But then you can apply power of gamma and x, and see that this geodesic that's spanned by x and gamma x is invariant under gamma. These are maximum concentration. Okay. Now, how to prove 2? If we have a hyperbolic isometry, and if you look at 2...
I'm not sure to understand why. I mean, you say in general in cat zero spaces, if you have a triangle which is really thin, then it's... what are you saying? What exactly do you mean? Suppose I have equality. Then you say that the triangle is on a geodesic, right?
What? Yeah.
I must know what you're saying.
I say that if you have equality, then the angle here must be exactly pi. Because if you have, suppose you have 2 lines going out of C1, it's a manifold, C2. You have 2 lines starting from the same point. The distance between C1 of t and C2 of t is at most 2t, right? What?
No.
The distance between C1 and t and C2 of t, it's increasing at most linearly. But at the beginning, you see that if the angle is not pi, then it's strictly less than strictly less than 2.
Obviously for other two it's obvious. I'm just thinking if Hadamard manifolds, you just know that this function is convex, so it's not true in any Riemannian manifold.
You
Right?
need Hadamard for unique
It is true in
midpoint.
any Riemannian manifold?
Yes.
It's the same thing.
Here I didn't choose the fact that it's an amount. This is,
You only use the fact that y is unique midpoint.
Why is there unique midpoints?
What?
The same.
Sorry?
But it's the same as y is very unique
Yeah,
point.
being Hadamard means y is a unique fixed point, because then you can
Yeah,
use
if manifold,
unique midpoint, not fixed point.
in Hadamard, the midpoint is well defined because it's Hadamard. But the argument that I say here, it's not about curvature. I mean, in any manifold, if there was an angle here which is not pi, then the distance will be strictly less than 2.
If the distance is small enough.
No, it's always strictly less. Maybe it can approach. What happened in hyperbolic space?
I mean, on the sphere, you might have a gamma y equals y.
But the sphere is not Hadamard.
No,
I know, but he's saying he's not using the pocket of the model.
You use Hadamard over and over again. Each time you
if it's smaller, it cannot be. If it's smaller for small t, it will be smaller also for large t. What's happened in hyperbolic space? If you take two geodesics starting from the same point, asymptotically the distance will be 2t.
Okay.
It will be, but it will never be equal to t. If there is an angle, it will always be strictly smaller. It will converge to the difference will tends to 2t, but okay, you agree with that?
Why is it strict for small t? Why is
For small t, it's like in the Euclidean plane. In Euclidean plane, if you have two segments that is it? And okay. Now, if isometry is hyperbolic, then it has then it follows that it will have some line on which it acts by translation, and this line is exactly the translation must be exactly the minimum of d gamma, because this line is gamma invariant, and the projection to this line shrink distance sense, so the displacement at any other point is at least the displacement on this line, by what we said before, right? You apply the lemma before to the line. Okay, if we have a hyperbolic element, then we found one line at which it acts on translation, and we say that this translation is exactly the minimum of the displacement function. Now, if you have another line on which it acts by translation, it must be parallel to this line, because the distance between them is constant. So look at the set of all lines which are parallel to. So look at all the space of all x's is decomposed. So the set of mean gamma, if gamma is hyperbolic, then mean gamma equals the union of all, let's call them x's. I never called them x's before, but x is the union of all, or if you want, the union of all geodesic which are gamma invariant and on which gamma act by translation. So this we already know. We know that it's the union of all x. The union of all translated geodesic. Let's call them let x is only afterwards. All geodesic which are gamma invariant and on which it act by translation. It must be the same translation, and they must be all parallel. And this set is convex, so this set must be isometric to a set W cross R, like we said before. And the action here is by translation, and the action here is just fix the point. So gamma acts to fix this and translation. So that's how hyperbolic hyperbolic isometry acts. Maybe I should give an example at some point. And part 3 was to say that gamma and gamma m are of the same type. So, what do you mean? So if gamma is elliptic, it has a fixed point, then certainly gamma to the m fixed the same point. If gamma is hyperbolic, then it has a geodesic on which it acts by translation, and certainly gamma to the m acts by translation on the same geodesic. So it must be hyperbolic as well. If gamma, vice versa, if gamma to the m,
Don't they just commute, like you said? Gamma commutes gamma to the m.
yeah, they commute.
And you said that if you have commuting isometries
No,
at the same type.
What are you referring now to something I said about negative curvature?
Mhm.
It's true in negative curvature if two things commute for the same type, but in non-positive curvature it's not true anymore. So it could be, for example, if you look at the isometry group of H2 cos H2, then look at 1 cos gamma 2 commute with gamma 1 cos 1, but this could be parabolic and this is hyperbolic. So you see, so it's not true in general that if two things commute, they are of the same type. But let's say that gamma to the m is hyperbolic, then gamma to the m preserves some line. So this line must be gamma invariant because it commutes with gamma to the m. And if this line, so gamma must be hyperbolic as well. And if gamma to the m is as a fixed point, then I claim that gamma must have a fixed point. Then, okay, if gamma to the m is a fixed point, then gamma has bounded orbits. And therefore it is a fixed point. So maybe it has less fixed points. It's not true that every fixed point of gamma m must be fixed by gamma. But if gamma... Okay, should I write it? Maybe I'm speaking too fast. Okay, gamma and gamma to the m are the same type. Let me give another lemma, and then we finished what I want to say about isometries, and then we have a break, and then we start to discuss groups of isometries. So the next lemma, maybe one definition, an isometry gamma of x called the clipboard if d gamma is constant. And this will imply that x decomposed to y cross r, and gamma acts trivially on y, and gamma is id insertion. So that's it for isometry, and actually I should the same applies to convex subset. So if I replace x by a convex subset of it, the same will be true. It's true in more general set as zero spaces. Okay, let's give another lemma. I will leave part of it as an exercise. So if gamma is parabolic, oh no, that's lemma is take some time to explain. Okay, let's. If gamma is parabolic, then there is z at the visual boundary of x, which is fixed, which gamma fixed Z and whole sphere, or around Z. Maybe I should define what is a whole sphere, right?
Sorry. So a Clifford is only defined for convex.
Yes. So if you have you can define a Clifford isometry for any space.
It's only true if it's convex.
But if X is a Hadamard space or a convex subset of Hadamard space, then Clifford isometry has such a different position. So okay, if gamma is parabolic, then there is point which is fixed by gamma, and also the Horo sphere. But maybe I should say what is a Horo sphere and Horo function, or Boltzmann function, which is the same thing. Okay, to do it rigorously, it will take some time, but let me summarize what we need to say. So Horo function are like, or Boltzmann function are distance functions, but from a point at infinity. So the idea is that if you like select xn in x, and suppose that xn converge to a point z at infinity. Okay? So you can look at the distance function from xn. So this function does not converge because if I look at one point, xn goes to infinity, the value goes to infinity. So let's normalize it. So minus d x0 at xn. Then the value of this function at x0 will be always 0. And this will converge if you want to a function which, let's call it hz, hz. The Horo function, this function, we call it a Horo function, surrounded around z. Of course, it's depend up by the choice of x0, but it's not really depend. It's depend only up to a additive constant by the point x0. If you pick another point, you will get the same function, maybe plus some constant.
Also, it doesn't depend on the sequence?
Yeah, it's independent. Yeah. Okay, tell you some facts without going. So this will be a whole function around the point z. Sometimes you would like to think of class of whole function, and you identify a whole function if the difference is bounded, or if one is the other, if they're equal up to a additive constant. And then every point at infinity corresponds to a unique class of whole function. And but I don't care about this. I take some normalization. I take some point and say, let's say whole function which are 0 at this given point, the origin of the symmetric space or the Hadamard space, and this will be a whole function. And this is the whole function, and the level set. Of hg are called Horo sphere. So if you want in the hyperbolic disk, if z is a point at infinity, Horo sphere look like that, like circles which are time channeled to that. Or in the upper half space model are just they look like constant altitude.
Only on infinity.
Yeah, that's the Horo sphere around between. The Horo sphere around this point will be some circle.
Maybe more like an egg.
No, we
Let's do this one.
you can do Möbius transformation replacing this point with infinity, and then it's circle will go to that. And so the level sets are called Horo sphere, and these are Horo function. And they have very nice characterization for a function. First, they give some compactification of the space, but they have nice characterization. So here is a fact lemma, which I will not prove now.
Oh. What about the level set of 0?
What?
It's only contain 1 point, right?
The level set of 0 will be the whole sphere containing x0.
Yeah, but why would it converge to 0?
Think about this.
Right.
Okay. Okay. So here is a fact. A function. This is called Boltzmann function or Horo function. A function f from x to r is the Horo function. Horo function hz for some z at x infinity, if and only if f is convex C1 and the gradient of f equals 1 at any point. Moreover, if you have two Horo function which has the same gradient at a given point, then they coincide up to a point. So this is a really nice class of function, and the definition is very helpful. So if you have a parabolic, okay, to do it systematically, I need to give at least one talk about Horo function, but I won't do it now. But let me explain how this fact follows. So look at the function d gamma. Here is the proof. This lemma. Look at the d gamma. This is a function which does not attain the infinite. So let's denote the infimum of d gamma by a. And look at the set. Look at define AT to be the set of all or define the function ft to be the function, the distance of a point from the sublevel set d gamma less than a plus t. The distance from some set. This is a convex set. This is a convex set. It's a sublevel set of a convex function. This is a convex function, sublevel set of convex sets. And I look at the distance function from this convex set. Now, letting t goes to zero, you see that these convex sets will go to infinity. Because the infimum of the function does not attain, any point in the space will, for small t, will be outside this set. So I get for I will have a convex set which are smaller and smaller. So if you want, if I draw the Hadamard space like this, I look at d gamma less than a plus t. This is some convex set. Maybe and for any point x, if I take this convex set smaller, if I take smaller t, I can guarantee that x is outside this set. So this set will for smaller t will be outside. Any point will be outside. So the function which is distance function from the set up to normalization. Let's again do minus the x0 from the same set. So normalize it. So you see that ft will converge to a Boltzmann function. It will converge to some function which is convex and has gradient equals to 1. Because a distance function, gradient equals to 1 is a property of distance function. So it will remain on the limit. And you will so you see that this will converge to a Boltzmann function. So since the sublevel set of d gamma is gamma invariant, d gamma is gamma invariant. So this set is gamma invariant. So ft is gamma invariant. So this function are gamma invariant. So the limit set will be gamma invariant. So we will get a whole function or Boltzmann function which is gamma invariant. So we'll get a fixed point infinity and the whole sphere. So this is the idea. Again, I did it a bit fast because I didn't prove all the background about the whole function that we need. The break is calling, but for us, okay, let's have a break. And I thought to finish with isometries before the break and then to speak about group of isometries. But I think we'll continue with isometries after the break and speak a bit about the group of isometries.